So as we take a look now at Module 5.2, covering static body stresses from Chapter 4 in our textbook, we're going to take a look at within this module are some stress analysis, some axial loading, St. Venant's principle, direct shear, single shear, and double shear. Now within this what we're going to do is go over the theory for these, talk about some of the key equations, some practical applications, and then go through some problem solving. So before we get started, I want to go through a sample problem here from some of the previous modules that we've been working on here in the previous chapter. So what we have here in the sample here is we tell us that we have a steel part. They tell us it's a 4340 steel. It's been heat treated, and they tell us now our hardness number, Burnell hardness number. So again, pay attention to what hardness scale they're giving us this in. So this is our Burnell hardness number, 300 BHN. Now what do they want us to find? They want us to estimate the corresponding values for our ultimate strength and our yield strengths, SU and SY. So as we begin this problem, the first thing we want to do, as in all our problems, is create our setup page, write down everything they give us and everything they're asking us to solve for, and then come up with a plan for attack or procedure for analysis on how to solve this problem. So now we read through the problem statement, we had an opportunity to take a look at what they've given us, what they're asking us to solve for. We want to create our setup page right here. So I have here, this is my sample number, sample problem 3.2. All the given information, well, they tell me it's a steel, AISI steel right there, Burnell hardness of 300 BHN, and it's heat treated right there. And they want me to find my SU and my SY for this here. So what assumptions can we make from this? We can assume that the experimentally determined relationship of SU to hardness is sufficiently accurate, so we can use that, as well as the fact that the experimentally determined relationship of SU to SY is sufficiently accurate as well. So now we have the information there, we made our assumptions, we know what we're looking for. Our next step is to begin our solution and take a look at our governing equations. So as we take a look at our solution here, our governing equation, we can go back to equation 3.11 of our textbook, which is on page 53 of our textbook right there. And I've copied that page out of the textbook here so we can reference back to it. There's our equation 3.11. That our SU is equal to KB times our HB right there. So if we have SU is KB times HB right there, then we have our relationship there. And our question is, well, what is our HB and what is our KB? Well, our HB is given to us in the problem statement. So now we just need to find our KB value right there. So for KB, what we can do is we can go down here below this equation 311 and we say for most steels our KB is approximately equal to 500. So that's what we use right there. For most steels, we're going to do KB is approximately 500 from page 53, and our HB is 300 BHN, which is given to us in the problem statement. So therefore our SU is equal to that 500 for steel and our 300 for our Burnell hardness. So our SU is equal to 150,000 PSI. So next thing we want to do in our process here is to solve for our SY. So we've already solved for our SU, so now we can go back to our textbook now to equation 3.12 on page 53 of our textbook. We find a relationship here that SY is equal to 1.05 times our SU minus 30,000 PSI. Now this is where our SU is equal to 150,000 PSI that we've already solved for in the previous section of this problem there. So we can take that value and plug it right back in here for our SU. Now we can see that SY is equal to 1.05 times 150,000 PSI minus 30,000 PSI. So we do that, plug it in, we find our SY now equal to 127,500 PSI. So that's how we can utilize those two relationships on page 53 in our textbook there in order to find our SU and our SY for a steel of a known Burnell hardness. So as we get started here, I want to do a little bit of a review on stress analysis. So what should we have learned and why? How are these stresses generated from different types of loading? So how are these stresses generated from axial loading, from direct shear loading, torsional loading, pure bending, and transverse shear loading? So we're going to take a look at all those, do a little bit of a review on how our stresses are generated from each of these forms of loading. So first let's take a look at axial loading right here. So we have a diagram over here where we can see we have an element over here, we have a column right here with an axial load P applied to the top, and we have a little mesh grid in there so we kind of see what's going on along the way. And again, we applied this loading, our load P, right here at the top of the bar. So within this here, first I'm going to ask ourselves, what is the stress state? So now we can take a look at our method of sections right here. So with our method of sections, you see over here on the right, we have just our element here with our load P right there from the top section where we took that section of it there. We made a cut right there at the section. This is our section CC. Then from there, what we do is we draw the reactionary force vectors at the section and surface. And we also draw in our moments down here as well. So we'll add those in right down there at the section. We can see, okay, there's our moment there, there's our force right there, our normal force right there, then we have our shear force right there. From there, what we can do is write out our equilibrium equations. So from these equilibrium equations, we can then go ahead and solve the problem. So from this free body diagram right here, we have all our moments and forces drawn out at the end of the section. We can write out our equilibrium equations and then go through and solve for each of those. So next for axial loading, what we want to do now is take a look at that normal stress that we were talking about there. So we have a general equation for normal stress that we've seen before in this course and some of our previous other courses such as ME14. So now we can over here, here's our section at CC right there still. Now we can see our x direction is going over here, and here's our applied load P like this. So what is our general equation? Well, our sigma in our x direction, if this is our x direction going right here, is equal to N over A, or in this case here, our load, our external load P, divided by our cross-sectional area of our section CC right there. So that's our general equation for our normal stress right there. So the force is equally distributed across the section. So that's what we can see here with all these arrows. This is showing that these are equally distributed across that section there. So it's isotropic and homogeneous, and there is no bending. One thing we can also do from this here that there's no bending is the force is through the centroid as well. So that's going to be very useful as we're simplifying down our solution. So now what we want to do is with this axial load, take a look at our deformation. So we can see over here, and this is why we have this nice diagram right here, which is very useful with all these lines on it right here, because now we can look at that deformation at each one of those lines. We can see we have our load P applied up here, our external load right there, and you see the load distorts the lines located near that load right there. So you can see right up here, that first line in A and B, you can see those lines distorting right there where it's near that load P. But then as we get down a little bit further away, these lines located away from the load and support, these remain straight down there. So what we can determine from this is there is a non-uniform stress and strain where the load is applied. So we're going to see non-uniform stress and strain up in this area rather than down here in some of these areas where we're seeing that these lines are remaining straight. So what we want to do now is take different sections. So corresponding with the A, B, and C on our previous diagram there, where we saw A and B, we saw some deformation at those lines there, whereas at C it was still a straight line. What we can do now is take a look at this axial load and how does it affect? Well, if our section was at AA, then we can see that we have going on here for our distribution, not uniform right there. A little bit more uniform as we get down a little bit further, but still some deformation right there at section BB. And then when we get down to CC, we saw exactly what we saw before, and this is an evenly distributed load right there. So next I want to talk about St. Venant's principle. So this principle here, what this is primarily saying is that the stress and strain produced at points in a body away from the region of the load application, so away from that load application area, these are going to be equal to the stress and strain produced by any applied loading that has the same statically equivalent result. So it has to have the same statically equivalent result and is applied to the body within that same region there. So another way to look at this here is if we take a look at that sample we just saw earlier a few slides ago, if you take your section far enough away from the point of the load application, as we saw in that member there, then the normal stress is uniform across that cross-section. So that's exactly what we saw. We saw it at A and B, we took the cross-sections there, it wasn't uniform. But then as we got down to C and below, then we saw the stress was a uniform cross-section, uniform across that cross-section there. So the general rule of thumb for this here is as the distance from the load should be at least the same as the largest dimension of the cross section. So again, this is just kind of a general rule of thumb. And notice this isn't exact, this is at least. So you might want to be on the safe side and go a little bit more than that. But again, at least the same as the largest dimension of that cross section for the distance of the load, the distance away from the load. Now we're going to move on to the topic of direct shear. So for direct shear, this is the application of equal and opposite, so still equal and opposite, forces that are also collinear, which causes the material between to experience shear stresses right there. So this is an average, it's not exact, but it's a representation or a summation. So we'll talk about that again. Not an exact, but we're talking this as an average right here. And another thing to note here is that the parallel to the applied force, we can use our V, our shear, to calculate our shear stress tau right there. Now we're only interested in the shear stresses in the plane of interest, not the complementary shear stresses. So taking a look at an example here, but now we can see we have a reactionary force down here. We have some object down there opposing this right here. So we have this bar right there. We can consider the bar with F is equal to R right there, where our applied load is equal to our reactionary force down there. Now what happens if we were to remove that? So if we remove that support piece from down there, then what we can see now is we have these shears right there, V there and a V there, that are opposite to our applied load F right there. So moving forward with that, we can take a look and say that from our equilibrium, what we can do here is we can use our general equilibrium equation, summation of forces in our y direction is equal to 0. So when the those are equal to 0, we can take a look over here at our free body diagram over here, and within that free body diagram, we can say, okay, what forces are acting in my y direction? Well, I have my force acting here down. Now, let's just say we went with a coordinate system like this here. So this is something that's important. We want to make sure we include our coordinate system. Unless we include this as a y positive down or x positive to the right there. So in that case, what forces do we have? Well, we have a positive y force and we have a negative v forces right there. So summation of forces in the y direction is say positive f minus 2v is equal to 0. We can rearrange that and then we come up with that f is equal to 2v. And from there, we can solve this for v. V is equal to f over 2. So that goes from coming up with our free body diagram from that initial given diagram, putting all our applied forces, applying our equilibrium equations, double checking our coordinate system right there, coming up with these, and then solving for our unknown or our interest, our shear force of interest. So from there, what we can talk about is summing up the individual shear stress for this direct shear. So if we look on the inside right there, we can have some element right here. We can see with that square there, it's got some delta V and some delta A for this area of it right there. Now what we want to do is we want to sum the shear stresses over one of these surfaces. So over the surface here, there's going to be multiple ones of these elements right there. So with that, we can have this relationship here, that our tau, our shear stress, is equal to this delta V over that area, the small area there, our delta A for that element right there. We can rearrange that and solve now, so delta V is equal to our shear stress times that delta A right there. So from there, if we say we can do that by summing those up, well, if we want to get more accurate result rather than just summing individual ones to get an average there, what we can do is we can integrate over the surface. So we come back to calculus here, and rather than doing a summation, we do an integral. So the integral of dv is equal to tau, a constant we can pull up front, times the integral over a of dA right there. So we can do out that calculus there. Integral of dv simply becomes v. The integral of a dA with respect to a right there, plugging that in for that limit of integration, is simply tau a. Now we can rearrange this, solve for our average shear stress. Our average shear stress here is our V over A. Now the assumptions we make for this here is that it's a homogeneous and an isotropic material in order to do this relationship. So going back to our example up here now, we can see there's our diagram there again. There's our applied load F. Again, we can do out our coordinate system right there, where y is positive down, x is positive right. X really doesn't matter for this case here, we're just dealing with the y direction. Summation of forces in the y direction equal to 0, so f minus 2v is equal to 0. Solve that, f is equal to 2v. Solve it for v, v is equal to f over 2. Now from that there, what we can say now that we have a relationship for V related back to our applied load F right there, we can plug that in now to this equation we just found from calculus right there, that our tau average, our average shear stress is equal to this V, which we can then plug in as F over 2. So plug that in right there for F over 2 right there. We end up with a relationship that tau is equal to F over 2A for our average shear, tau average. So this brings us now back to direct shear again here. So shear stress acts in the direction of the shear force. If we look at that there, there's our shear stress, our tau average. There's our shear right there. So this is acting in the same direction, and both of those are acting in their opposite direction to our applied load F. So again, if we called y positive going down, then F would have a positive value, and our shear stress would both have negative values associated with that. So from there, let's take this a little bit further and take a look at two different cases. A single shear, a little bit more simplistic case, and a double shear. So for a single shear, the applied force is transmitted from one member to only one other member through a shear connection. But now if we're dealing with a double shear, then this applied force is transmitted from one member to two members through two shear connections right there. And that's going to be important as we're drawing out our free body diagrams and doing our equilibrium equations. So let's take a look at the shear stress. There's two different cases of a shear stress right here. One, you just have these two boards, one on top of another like this. You have your applied loads going out in this direction here. The other case, you have those same two boards, but now you've got a pin going through for a pin connection right there, connecting them together. So for these two cases of single shear, let's take a look at some of our governing equations. So we take a look at this here. Okay, there's our board right there. We're just interested in one of them right there. And we can see this is where it overlaps right here. Has some distance x and some distance y right there. We know that the shear right here is equal to F. We've shown that in our free body diagram or equilibrium equations before. So we have that there. There's our equilibrium equation. Where our summation of forces in our x direction right there. There's our x direction like this here. So we have a force and we have our v right there. Again, what are we considering positive and negative? Maybe we're considering x positive to the right, y positive going up right now. So if we have our x positive going over to the right there, well, then this F is going to be positive, this is going to be a negative V, so F minus V equals 0, or F is equal to V. So from there, we can now say, well, we also need our cross-sectional area right here. So for our cross-sectional area, what we can do is we can say, oh, this is x times y, base times our height right there. It gives us our cross-sectional area, which then gives us this relationship shown here for our average stress right there when we plug in for A being x, y. So now let's take a look at our other case for shingle shear here, where we had now this bolt hole right there going through it right there, where we have that bolt going through connecting those two planes together. So again, we still have our external force F acting over there. Let's just call this the same thing. Positive x going this way, positive y going up like that there. We have this over here being our B is equal to F. We can get this now. We take a look at our equilibrium equation. Summation of forces in our x direction right there would be a positive F minus V. So F is equal to V in that case right there. So now we can say, well, our area is going to be different now. Our area here is now going to be for this hole right there. So area of a circle is pi r squared. Don't forget, if we're dealing with diameter, if they give it to us diameter, it's d over 2. So we put that value in there. Then we go back to our average shear equation, which again we found to be V over A. Now we plug in a different area because it's the area right there, that cross-sectional area. Plug that in for our A there, and we end up with is our tau average is equal to F over pi r squared. Now next what we have here is a double shear. Well, again, we'll look at two cases for double shear. But let's for our first case, let's just look at the simple case here, where we have our two boards sandwiched between, one board sandwiched between two other boards there. We pull on this guy here, we have our F going over here. Then we have our F over 2 and our F over 2 for that there, where if we just look at our free body diagram of our center board right here, what we can see now, if we pull out on this in the F direction right there, then this is going to be F over 2, or our V's over here, where that shear is equal to that F over 2 from this relationship we've shown here. So now, from there, we can go through and do our equilibrium equations for this. So we start with that free body diagram right there. Again, we define this overlapped area as our x, y, and realize that now it's on the top and on the bottom for this here. So we know our area is going to be x times y there. Let's take a look at our summation of forces from our free body diagram. Again, we'll draw our coordinate system here, positive x to the right, positive y up. What are our forces acting in our x direction? Well, we have here acting in our x direction right here, an F and a negative FV and a negative FV right there. So we can do that there, or negative 2V right there. So we can do that there and say our summation of force in the x direction, we have F minus 2V is equal to 0, or we can rearrange this and say that solve for V. V is equal to F over 2, and we know again our area is equal to XY from our relationship right there. Then we can come back over here, and what we realize now is that there's two of those there. So if we plug into this relationship right here, V over 2A right there, V is now F over 2 from this relationship right there, and our area is still that XY. So we plug that in right there. And now for our double shear situation here, we have tau is equal to F over 2XY. Now we can look at our double shear case for when we have the pin involved right there. So we can see there's our force going off to the right there. There's our F over 2 and F over 2 over there. And then we take a look at just our centerpiece right there. We can say, oh, there's our force there. Draw our free body diagram. Our V and our V right there, which is F over 2. Equilibrium equations, X in the positive direction here. If this is our positive X going over like this right there, then we can say summation of force X direction. We have a positive F minus 2V, or V is equal to F over 2 again right there. Then we can say, well, now our area is based off that circle right there, so area is equal to pi r squared, or there's diameter pi d squared, or pi d over 2 squared. Plug that into our tau equation for our shear stress. Shear average is equal to our V over our A right there, our shear over our area, where our area is this pi r squared. We can plug that in there, and our V right there is equal to F over 2, so we can plug that in for our F over 2 there. Once we plug that in, we found that our tau average is equal to F over 2 pi r squared.